More than asking what, it is important to know how things happen, how to proceed in learning, how to learn general relativity, how to understand the mathematics, how to select the book, how to know which book is the best. Now, in order to answer all these questions and to clear all your doubts, this is one single video which will clear all the confusions and complexities. This video is your one-stop solution study guide about general relativity, everything that you wanted to know about relativity, books, mathematics, resources, and everything. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to this video. All you need to know about general relativity from the mathematics, resources, concepts, and so on. First, we need to understand what actually is general relativity. Now, if you look into this figure, you will understand that general relativity is nothing but a geometric theory of gravity developed by Einstein and others. Now, it was published around 1915, almost 10 years after he framed his special theory of relativity. General theory of relativity actually, I would say, redefines and refines Newtonian mechanics. So what you see right on the screen is that Newton's famous laws of equation, that is the gravitational constant G and other equations, actually got, I would say, redefined and generalized into what is called a space-time curvature. This space-time curvature, as you can see, further got generalized and got further options to study in terms of cosmology. So all the extreme objects of nature, which are white dwarf, neutron star, black hole, these are actually studied through Einstein's field equations and are generalization of further study in cosmology. What we know as straight lines as the distance between two lines in Euclidean and Newtonian mechanics got further generalized into what is called geodesics. Geodesics are a kind of a generalization or similar to something which are straight lines in Newtonian mechanics. Also, the concept of space and time, which was quite two different identities in Cartesian coordinates and Newtonian mechanics, further got generalized into something at a single lump, and that is called the space-time continuum, where space and time is united into one single identity. This is what is called the Einstein field equations, and we will look into that. Comprises of 16 partial nonlinear differential equations. These equations actually led to the formation of stress energy momentum tensor and various other tensors. And with this Einstein field equations, we actually study what is called a space-time curvature. So this space-time curvature actually led further into the study of cosmology, black holes, gravitational time dilation, and gravitational waves. So in general, this is what we call general relativity. But whenever you look into the picture of general relativity, or when you search about general relativity on the internet, you come across pictures like this. These actually are a pictorial and a schematic diagram of what is called general relativity. Now, some people say that this is not correct or this is not a purely mathematical description, but I would say both of this and this is correct, because all this, what it does is that it gives you a fairly intuitive and an overall idea of what is general relativity. That means it shows that there is a heavy object somewhere lying on a kind of a trampoline, and it creates a dent, and this dent is on a grid. Now, the question is that when you search with the word general relativity into the internet or on Google, what you get is a kind of a definition like this, which comes across first, that it is Albert Einstein's theory of gravity. In Wikipedia, it also shows more or less the same, but it gives a much more detailed idea that it is based on 1915, the current description of modern physics, generalization of Newton's gravity, so on. Further, Britannica also gives you something related to similar to Wikipedia, and New Scientist also gives that it is a theory of Albert Einstein. So what I'm trying to tell is that all want to 3-4 definitions of general relativity. When you search in internet, actually it talks of one single thing. What is that? It is a study on the curvature of space-time caused by the presence of mass and energy. That means somehow it is related to the geometry, and that geometry is actually caused, or the dent or the change in the geometry or the trampoline that you saw is caused by the presence of mass and energy, and this is actually a curvature of space-time. Now from here, what we can understand is that general relativity is a total shift from the usual mathematics or the usual mechanics, that is, and that is what we call, that is a geometric understanding of space-time. That means what? That we need to understand more of the geometry, and for that there is a kind of a shift in terms of understanding. So when we talk of shift, we talk first about special theory of relativity, because that is basically on which the general relativity is based, or basically that was the first theory of relativity. So initial frame of reference, it deals with speed and velocity. It deals with frames of reference. It is experimentally provable. So from here, what we come to know, that special theory of relativity is nothing more than what is called the study of relativity and simultaneity. That means it basically speaks of speed, time and space. Now when you look into general relativity, you see a totally different picture. There's a paradigm shift, and this paradigm shift is because it deals with non-inertial frames, gravity, geometry of space-time on a much more larger scale, that is on Earth, Jupiter, black holes, galaxies, etc. So it is not a study of relativity anymore. It is a study of geometry, and this means that it is a study of curvature of surfaces. This leads us to the final conclusion that it is more of geometry and less of relativity, because as we saw previously a few seconds earlier, that it is basically the study of the nature of the curvature of space-time. And how do we measure those curvature? It is through different tools of geometry. So when we talk of this, that it's a geometric understanding of space-time, that means there is a mental shift also in terms of the preparation. And in this part of the video, I will just tell you what is the mental preparation that you need to have in order to understand that. So when we talk of mental preparation, it means all those factors. An abstract visualization, you need to have a strong visualization, logic, and there are very geometric transformations, because you see from the flat space, from the Euclidean space, from the Newtonian mechanics, we are now moving into a much more abstract world where visualization really matters. And that is why I tell that GR, or general relativity, is more intuitive in nature rather than mathematics. Obviously mathematics is there, but as you start understanding geometry, you start visualizing that. Now, having said and understood what is general relativity, what is the mental preparation, and what is the shift in terms of mathematics to geometry, now the question comes is that what is the mathematical tool first, the first step that you need to know in order to understand general relativity, coming up into the next part of the video. So the first thing is what you need to know, calculus, and that is single and multivariable. Now, why we need calculus? Let us first quickly understand that, because calculus is fundamental to general relativity, because everywhere you will find those differentiation. Now, say for example, I was talking about geodesic. This is just a straight line which is generalized on a curvature of space-time. You can see these all contains differentiation. Even if you go further and you take complicated metrics like Schwarzschild metric or the Robertson FLRW metrics or the Kerr solution, you will always find there is a high level of differentiation that you need. So Einstein field equation, even which forms the core and which is the guiding power of general relativity, is nothing more than a set of partial differential equations. So this is the reason why we need to know calculus very well, and that brings us to the question that why you need to learn calculus to understand general relativity, coming up into the next part of our video. Now here you see I have already defined that Einstein field equation, which is fundamental to general relativity, actually is nothing but 16 reduced to 10 nonlinear partial differential equations. So what you see right in the screen is not one equation but a summation of 16 partial differential equations. So these are 16 partial differential equations. If you need to really understand them, then obviously you need to know more about calculus. So partial derivatives, for example, gravitational potential in Newtonian mechanics, and when it got generalized into partial derivatives of the metric, these are nothing but partial differential equations. Now further you can see these huge calculations which I have actually made in one of the videos. This is nothing but actually the derivation of the metric tensor, which actually measures the causal structure of space-time. Now all this dx1, dx2 and g11, these are nothing but partial differential equation. As you can see right on the screen, this is a huge kind of a derivation of partial differential equations, and that actually shows that why you need partial differential equations to know. So if you further see that when these equations got substituted and finally what we got is the metric tensor, it is nothing more than what is called the partial differential equations. And if you're really curious to know how this derivation etc. happens, this is the video which I made around 2 years back. It is fairly extensive. It contains all about metric tensor, general relativity, and how you can understand the derivation of partial differential equations. So here we actually prove that why partial differential equations forms an integral part in our learning process of general relativity. The next question comes is that we understand partial differential equations etc. But what are the which concepts of PDEs? Here you will learn more about PDEs related to general relativity coming up into the next part of the video. Now you see the linear and non-linear partial differential equations, because general relativity involves both linear, because in weak field approximation, that means if you take gravity and other things moving slow, they actually turn back into Newtonian mechanics, and from Newtonian mechanics again you can go into Einstein field equations. So these are all PDEs. Also you will see I have just made a video very recently talking more about the elliptic and hyperbolic geometry. So the elliptic, parabolic and hyperbolic geometries all are basically a part of general relativity. If you're talking of hyperbolas, the light cones, the Minkowski light cone, the space-time diagram, all these are basically made out of hyperbola or hyperboloid or hyperbolic curves. So you need to have an understanding of these things, because this would help to categorize the type of equation. So gravitational waves is hyperbolic and so on. So that is why you really need to know PDEs very well. Also the fact here is that the stability and well-posedness, because ensuring that the solutions of the PDEs are stable and well-posed, it is important to understand gravitational partial differential equations. Now also there is something which is called existence and uniqueness of the theorem, because under PDEs, under certain conditions, these theories or these theorems really work out, although not directly, but it is very important that you understand partial differential equations in a very comprehensive manner. Now when you talk of partial differential equation, the next question which comes to your mind is that how I am going to learn. So here are some of the books on calculus which are going to help you tremendously. There are many books. However, I would like to start first with this book, which is called Thomas Calculus. It is a round about 1,000 pages book, but it is good. It is very extensive. So here is a quick review on the book. It is one book that teaches you everything. You really don't need to go anywhere else. The book contains a lot of simple illustrations, examples, diagram, and it actually assumes that you know nothing, so that it teaches you step by step everything that you need to know about calculus, starting from ODEs to PDEs. Here is a quick glimpse about the content of the book, which you can see. It starts with functions, applications of derivatives, limit and continuity, infinite sequence and series, and so on. Although it is a very detailed content, I cannot cover up in one video, but this actually gives you an idea about how detailed this book is. Now if you are an absolute beginner and you have absolutely no idea about calculus, then this would be a Bible for you. Sylvanus Thompson's I would say book on calculus. This is absolutely for beginners, but remember that partial differential equations are not much covered. It is an absolute step by step showing you through geometry and simple figures how to understand calculus. It is very simple and a quick I would say guide to learn calculus. This is much more mathematical, and it is an old book, classical book, Piskunov's Calculus. We read it during our college days. It's one of the best introduction to calculus. It ultimately considers around 150 to 200 questions, and it is, remembered, it is a single variable calculus book, so it will cover up everything that you need to know. It's much more mathematical in nature. The second book would be this one, K. Sankara Rao's partial differential equations. I'm talking more of PDEs because in order to understand general relativity, you need to have a better understanding of PDEs. So it also helps you to clear up examinations like NetGet. Also, it is user friendly, containing lot of examples, so it is a very good book to go through. The next book from my recommendation would be this one, Partial Differential Equations by Yehuda Pinchover and Jacob Rubinstein. And remember, when you're selecting partial differential equations, one thing is that it might contain a lot of engineering applications, because PDEs are related to engineering application. So you will have to be quite aware about that. And this contains nice exercises, and Yehuda Pinchover is a big shot in terms of mathematics, so you can go through that. Yes, it gives you both skill and confidence. Another quite important book is Introduction to Partial Differential Equations, and it includes weak field solutions, non-linear PDEs and Burger's theorem, etc. So it is a very good book. It is by Peter J. Olver, Introduction to Partial Differential Equations. As you can see, this is also a very detailed content, and I've just given you a glimpse of the book so that you can go through it. So these are few of the books, but I'm not done yet. And the question still comes that, can you summarize, or what is the real reason of understanding ODEs and PDEs for knowing, I would say, Einstein field equation? So understand that because Einstein field equation are a set of 10 partial non-linear differential equations, because PDEs are used to express the relationship between stress energy tensor and Ricci curvature, because many solutions of the Einstein field equation cannot found analytically, and that is why we need PDEs, and because it involves four-dimensional space-time as a single manifold, and again because solving these PDEs for specific solutions can actually predict how space-times can be curved, etc. That is the reason you need to understand partial differential equations. So the first step in the mathematics of understanding general relativity is a good mastery of partial differential equations. Now remember, this is actually what I have shown much more detailed in one of the videos, which is this one. So this video is actually collection of those 5 videos which I have made earlier in one sense. So if you want to learn more about PDEs and much more detailed understanding about the books, etc., I'm giving you the link sequentially in the description box. You can go to my playlist and check out this particular video, and it will make you understand about how to learn the mathematics for general relativity. Now, apart from PDEs, what is important is the second thing, which is called linear algebra. And into this part of the video, we will talk about why do you need linear algebra in order to understand partial differential equations. The Einstein general relativity. Now, when you understand and when you look into what is called linear algebra, you really see through those kind of things. And these really look like matrices, isn't it? So we have got the matrices, the indices, the operations of matrices at one hand, and on the other hand, you see these things in general relativity. So the question is that what is the relationship, how the matrices are related to the matrices in general relativity, and why linear algebra is important? Or you might ask, is linear algebra at all important to learn general relativity? That is what we are going to look into next part of the video. So here you can see that why do you need linear algebra? Because linear algebra provides a framework for vector operations and to calculate, describe velocities, momentum, energy density. So here you can see this is a metric tensor which actually comes from the linear algebra part. So the metric tensor is basically nothing but the inner product on the tangent spaces of manifold, which is something which is the bilinear form of a linear algebra. Again, the Ricci tensor, what is that? Ricci tensor is basically a summation of indices of the upper and the lower indices, and this is actually done through linear algebra. So we see that as we proceed into the core mathematics of Einstein field equations and general relativity, linear algebra forms an integral part. Here you can see even in the metric tensor, certain portion, as I told, these things gets cancelled out. And in general relativity, what we get out of the 16 components, 6 components gets cancelled out, and that is done through diagonalization, and we get what is called the 10 components of metric tensor. Also, you see the metric tensor is symmetric. What does it mean? We will come later, but this is again linear algebra, and metric tensor gives the causal distances. That is, all those distances between those red points, as you can see from here to here, these are all done by linear algebra. This particular tensor, which is called the stress energy momentum tensor, which we will cover later, that means the amount of stress or the amount of energy, whatever is there, this is in a kind of a matrix, and this again crops out from the concept of linear algebra. So you see that linear algebra is around everywhere. All these matrices which got generalized into tensors, how does it come? It all comes from linear algebra. So from here what we understand is that vectors in general relativity is denoted. So the length of the vector is given by this, that is linear algebra. The diagonalization, it comes from linear algebra. So that is how it is written. The metric tensor, which is formed from the inner product, and inner product crops out from the concept of linear algebra. Even the volume element, which is a little bit technical, also come out by calculating the determinant of certain equations, and the change in its volume is also coming from the determinant. All these are actually taken from linear algebra. This is the video which you can go through, which I have made, lesson number 12, if you really want to know what is volume form and volume element, and how it is being derived. So overall we can say that these are the things which are related to linear algebra. Now the question comes that this is that all these concepts are inherently related to linear algebra, and this shows the reason that you need to understand linear algebra, and gives you a kind of a objective and a good reason that you should know linear algebra in order to go ahead with general relativity. The question is that, okay, do I need to understand all the concepts of linear algebra, or there are certain other concepts of linear algebra? So first let me tell you what are the concepts which are related to general relativity. First is that you need to understand what are called vector spaces, because all the vector spaces which got generalized into tangent spaces, it will come in general relativity, so you need to know. Obviously matrices and matrix operation, because how will you then contract and how will you make the things happen without knowing the matrix operation? Inner product and norm, again very important, because the metric tensor itself forms the inner product, and many other operations. You will see inner product is terribly important for general relativity as well as for quantum mechanics if you are learning that. So these are the concepts which are very important. Diagonalization and orthogonality, linear transformation, because Christoffel symbols and other things are linear transformation, and the symmetric and anti-symmetric matrices, because you will see that what is a symmetric matrix. Then again you can see that the electromagnetic field tensor, which is an anti-symmetric. So in order to understand everything, the nature of these tensors, etc., you need to know linear algebra. Coming to the next question, that how will you learn? The books of linear algebra will show you some of the most important books. The first would be this book. I'm not going through Gilbert Strang, I'm coming to that, but I would recommend first to go through this book, which is about Howard Anton and Chris Rorris, Elementary Linear Algebra. This is, I would say, one of the best books. It gives you a geometric intuition and an understanding of linear algebra, and I would recommend first to go through this book. Now you see I have underlined few important parts. What are the hallmark features of this book? Because linear algebra is a cohesive subject and is not simply a collection of isolated definition. A transition from Rn to generalized vector spaces, sometimes it becomes important. So the authors have done considerable effort to devote it to explaining this. Also you will see the mathematical precision proofs are presented in a patient style that is tailored for beginners. So it is all for beginners in a very easy way. The next point, you can see that to serve the needs of the students of engineering, computer science, biology, physics, business and economics. And that means if you're not majoring mathematics, you can go through this book. It is going to be very important. And also there are a lot of historical ideas and real people who created these equations and the mathematics that is also covered. So all in all, it is a very good read of this book. Also you see here that the book has been made into these chapters, and even the long template, short template for the teachers is also done in a nice way. So it is around 1276 pages, but fatter the book it is better, because it teaches you right from the beginning. The next thing which comes across is Gilbert Strang, the famous book, I would say a legendary book on linear algebra. I really don't need to mention most about that. One of the greatest mathematician and teacher, I would say, at MIT. So all these things are covered. Transitions to classical linear algebra, lot of easy exercises, then turning from here to other, etc. So it is a very good book. I mean to say, I think you have all gone through. And this is an overall content of this book. I think it will take quite a time to go through. So it gives you the enough confidence and motivation. It teaches you right from the beginning. So you really don't need to worry about that. The next book which comes is Linear Algebra Done Right. This is also a very good book which you can go through. It contains a lot of beautiful diagrams and the content is very exhaustive. So you can see this is basically the content which covers starting from vector spaces, linear spaces, all you actually need to know about linear algebra. On a lighter note, I would say not too much mathematical in nature would be Schaum's outline of linear algebra. As you can see, this is also used for UPSC, JRF and NET, and if you're a beginner, definitely you can start with this because you can clear the further competitive examination with this. Schaum's book has got a very exhaustive content, and you can see it starts from chapter 1, algebra, systems of linear equations, canonical forms. This is very well illustrated, a lot of good illustrations, etc. there. And my final recommendation would be this book by Bronson and Costa. This is also a very good book, not very thick in nature, but it gives you a very good understanding about linear algebra. Again, coming back, this is the second video where I have covered much more amount of books. This is the part 2. I have given the description. You can go and understand. This video contains more about the specification and details of linear algebra and its relation to general relativity. The third and the most important thing, which is perhaps the pivotal force of general relativity, are tensors. So in this part of the video, first we will look into tensors and general relativity, coming up into the next part of the video. First, let us understand that all these things which we have seen, stress, energy, momentum tensor, metric tensor, electromagnetic field tensor, all this along with the linear algebra part that we have just seen actually forms the mathematical foundation of tensor. So the question is, what is a tensor? What pivotal role it plays in general relativity and why it is important? All these things and how to understand them. These are the things which we are going to cover into the next part of the video. So first let us understand in general overall that what is a tensor, although it will take a long time to cover it. But tensor actually comes from the Latin word tender, stretch, and in anatomy also it is used for muscle that tightens or stretch, and it has got something to stretch and pull. So from here what we understand that if we get a sphere and we stretch it in an oblate spheroid, so if there is some amount of physics or some amount of data which is happening over here, it gets stretched over there. So and how do we come to know about that stretched information? That is what is the rule of tensors. So you can see that it is a set of components of the coordinates and that transforms linearly. That means it takes a certain mathematical rules to transfer, and this is basically registered through the usage of tensors. Here is a much more pictorial understanding. If I get a kind of a coordinate like this and then I stretch it over this, and if I get a data over here and it gets stretched out over there, how do I understand? When I move from the transition from flat space to curved space, the same thing happens over here from sphere to oblate spheroid. The object is stretched. How about a coordinate which is rotated around here? The data also gets rotated, but how will I understand and measure them? So the basic thing is that how do we measure things and how to change the measure the change in spite of the coordinates being changed. That is basically is the idea of the tensors. So the laws of nature should be invariant as put up by Albert Einstein also, that irrespective of the frames of reference we should be able to measure the laws of nature, and that is why the tensors come in. And you can see the tensors form the pivotal role of Einstein's field equation. Now, if I try to explain this equation in a very simple language, you will see there are certain things which you already know. Lambda, which is a cosmological constant. C, which is the speed of light. 8 pi, which is a constant. And G is again the good old Newton's constant. Now, what remains unknown are these factors, which are variables or which we really don't know. And here I would like to explain you quickly what are those factors, although I have explained it many times in detail. So these are all constants. So what becomes important is the first R, which is called the Ricci curvature tensor. It's a kind of a measurement that how things actually change from flat space to curved space. The next R is also called the Ricci scalar. It keeps track of how a ball, a kind of a sphere, it deviates from a Euclidean space to a Riemannian or a curved space. The next one is this G, which is important. We have seen that it is called the causal distance of measure of space-time. One thing which is hidden is the Riemann curvature tensor. It is the tool used to describe Riemannian manifolds. And the last thing is this T, which is the matter movement through space-time. That means if a matter is moving through space-time, how do we understand that? And if you want to know much more in details about all those equations and the mathematical part, you can look into lesson number 21. Which is an elaboration on Einstein field equation. So we understood what is a tensor. And the question is that what makes tensors so unique? So the answer to this is that you can see that if I take this kind of a frame of reference and I rotate the frame of reference into the right hand side of this photograph of this illustration, so this AX and AY in the original figure gets stretched into A prime X, and A prime Y becomes a little bit smaller, isn't it? So this change is being registered through tensors, which is called this metric tensor, which you can see right on the screens. Now the question is that this is how the origin of tensors or the role of tensors actually comes. Now the question is that how does it play? So that this static frame of reference and the rotated frame of reference, you see something has become bigger and shorter, but we need to mention the vector which should be invariant. So what is the role of tensors in general relativity? If I ask you, obviously it is measurement. Let us see how we can understand that. So here is a flat surface and here is a straight line. Now coming to a curved surface, you will see this straight line will become curved. What does that mean is that the usual Pythagorean rule or the distance between 2 points is not going to work. And we need some kind of an exotic mathematics which is called the metric tensor, and that is what it does. It computes the length, the infinitesimal small distances, tangent vectors, and so on. This is actually the role of the tensors. Now, as you can see that there is a concept which is called a covariant derivative, and I'm right at this moment skipping this part because it would be too technical to explain, but again I will show you the video link which will explain you what is a covariant derivative. So this is basically again the Ricci tensor and the Ricci scalar. All these things actually describes a general relativity in an invariant nature. So if you see that what is the Ricci tensor, you can see if I move a ball along a straight path, it has got a zero curvature. So Ricci tensor is equals to 0. Along positive curvature, when the ball shrinks inside and the ball increases inside when it has got a negative curvature, Ricci curvature is less than 0. If you want to know more about this, you can go to this very old lesson of mine where I have already explained about Ricci curvature tensor and so on. Coming back to part that how do tensors make your life easy? Now you can see this is an Einstein field equation. Any component of Einstein field equation, it has got 16 components which looks terribly messy, and it can be it can be huge like this. Similarly, the stress energy momentum tensor. So if I want to write this exhaustively, it would be like this, this, and this. So in order to write that, we use the tensor notation, which can be simply written as this, and this is actually the component which has got 16 forms. I have written it just in one single notation. Understood all this, you might have a question that what are the books that you need to learn about tensor calculus. So the first and the most easiest book would be Daniel Fleisch, Vectors and Tensors. It is the most easy book. You can pick it up at any point of time and just start reading. So this is the book about vectors and tensors, and you can see already you are learning a lot about metric tensor, Riemann curvature tensor. So you're learning general relativity. The second book would be this one, the G.E. Hayes Vectors and Tensor Analysis. This is also a good amount of book, and you can see mixed tensors, invariant, contravariant. I mean to say the general tensor part is being covered. So it is quite a book to understand. The third book would be based on physics, because tensors we are learning on for General Theory of Relativity, and this would be Tensor Calculus for Physics by Dwight A. Neuenschwander. It is quite a good book and deals with a lot of physics. If you're interested to know more about the mathematical part of this book and the content, you can take a pause of this video and you can see what are the things that are being covered. Although this is not exhaustive, but it's a very good book to read. The next would be Tensor Calculus and Differential Geometry by Prasoon Kumar Naik. This is also a very good book because it contains a lot about Christoffel symbols and things like that. I mean to say it covers up a lot of things, so you can definitely learn from this. Again, as this video is an assimilation of several videos, so here you see Christoffel symbol is being covered, Riemannian geometry. So the third video you can go in much more details, the role of tensors, origin of tensors, and many more mathematical things which is there. It is called in the third part. I have given the link. You can go ahead and check it. Now, apart from tensors form an integral part. Now, another thing which is mathematically very important is this differential geometry, and we will look into this part in this part of the video also, because differential geometry is essentially a very important tool. First, let us understand that what do we mean by differential geometry. It is a sum of two words, differential, which means actually using calculus or infinitesimal, finding out infinitesimal differences and the rules of calculus, and geometry means basically that we are applying the rules of calculus on the surface. So differential geometry is basically a branch of mathematics which uses calculus to apply on geometry, and these are used to analyze and understand derivatives, tangent spaces, connections, and things like that. That means it is using calculus in order to know the curvature of space-time, and that is geometry. So here you can see that there is a shift, that is from flat space-time we move into curved space-time, and that is what differential geometry registers. Let us look quickly into the next part of the video. So as you can see, the Newtonian mechanics deals with flat space-time, and it is where it is unchanged. And the second thing is the curved space-time, because general relativity deals with curved space-time, and this curvature depends on how the mass and energy is changing, because more massive object like stars will create a kind of a more curvature rather than the other. So differential geometry is a tool which actually describes and analyzes these curved spaces which happens on manifolds. Now hold on, I'm going to explain you very briefly what is called manifold, but before that, this geometry actually is responsible for causing that gravity. This is called geometry of gravity. As in Newtonian mechanics, gravity is like a force which is like electromagnetic force of magnets which attracts each other. On the other hand, general relativity completely presents a different picture. It's a manifestation of curvature of space-time. So this curvature is basically is not just a dip. It affects how things move in space-time, and these are called geodesics. So more massive the object, more is the space-time curvature, and this is actually explains why light bends around stars. This is not explained in Newtonian gravity. Now the question terms is that the role of differential geometry obvious in general relativity, and this is quite evident because here you see that differential geometry provides the necessary tools to analyze the curvature. It gives you a precise calculation. It also allows you to describe the relationship between the mass energy and how mathematical object tensors. So most of the books of tensors contains a lot about differential geometry. But remember, this trampoline example is not actually perfect. The reason is that space-time is not just 2D, it is a 4-dimensional manifold, and for the higher dimensions, differential geometry actually allows you to define those higher dimension fields. Now, why do you need differential geometry? Here is a pictorial and a clear understanding which will make you understand. Now, you see, differential geometry, as you understand, deals with the understanding of the curved surfaces, etc. So here is a curved surface, and this is where, on the other hand, this is the curved surface, and this is where the physics is taking place. So from on the curved surface, if any physics is taking place, to analyze the notion of that physics on the curved surface, we need the differential geometry part. So from curved surface, we move into the physics, not from physics to curved surface. I mean to say that is how the order happens. Now here you see these are all actually the curvatures. This has got a converging curvature, so it is positive curvature. This has got parallel lines, so this is a zero curvature. Here the lines geodesics are diverging, so it has got a negative curvature. And if I take all those curvature in a single piece and I start differentiating, that means dividing into small part, and use calculus, then we are just using the rules of calculus on these surfaces. That means to calculate the curvature. Now this is pretty important, and this is basically gives you an idea about differential geometry. The next thing which comes is very important. So here you can see these lines are called locally Euclidean. That means if you magnify that, it will look like ordinary space, the ordinary Euclidean geometry. And this is what is called the concept of manifold. Very important, manifolds and general relativity. I will try to explain it in the next part of the video. So here you see that when you get the manifold actually forms the basis of general relativity. If I zoom this, then what I get is a locally Euclidean. In the sense, locally Euclidean means it is just a local space where you can use Euclidean or calculus to analyze them. So manifolds actually provide the mathematical framework, and manifolds can have different dimensions, because a beach ball can have one type of a direction, but in space-time it has got 4 dimensions. So what we understand is that manifolds are defined mathematically using the concept of homeomorphism. A homeomorphism is something technical which I am not explaining. It means that, for example, a donut and a coffee cup are homeomorphic. That means they share certain important features. Or you can say that they have got certain features which are common in between. I will show you quickly that what I mean by homeomorphism. So imagine that these are the 3 figures. A box which is blown into a further figure and it goes into a kind of a ball or a beach ball. So if there is a physics happening around here, and if we study that manifold, as we say locally homeomorphic, that means the same thing will have a same feature around here and the same thing will have a same feature around here. So from there we can say that because all of them have some common features, because they are manifolds and they are homeomorphic, you will understand that the physics are happening around there also shares some common features, and that gives a tremendous advantage for mathematician physicists. If we learn one surface, we can understand the physics of the other surfaces also, because they are locally homeomorphic. The question is that what are the best books on manifold? I will come to the differential geometry part. The first one is this book, Loring W. Tu's Introduction to Manifold. This is a great book. For the beginners, I would say this is excellent. You can go through. And the next one is Introduction to Smooth Manifolds. This is also a great book by the famous John M. Lee. Nothing more to tell about this. This is an absolutely excellent book to learn on manifold. We come now to the books on differential geometry. There are pretty good number of books. The first book would be this one, because this is the first book to learn about curves and surfaces, and most importantly you see that it assumes that if you don't know algebraic topology, it is okay, because it doesn't consider algebraic topology. So you can very well go through this. The second book which I would recommend is Andrew Pressler's Elementary Differential Geometry, a great book to go through because it is one of the clearest and very simple. Anybody can understand that. The third book which I would say is Christian Barr's Elementary Differential Geometry. This is also a very good book to go through, I mean to say, for the beginners. And the next book would be this one, which is, I would say, one of the greatest, and I would say a kind of a Bible, is Elementary Differential Geometry, Barrett O'Neill. It is very clear and very, I would say, crisp and clear, and anybody can understand. The next book is a little bit exhaustive, and this book gives you a kind of visual demonstration of differential geometry. That is Tristram Needham's Visual Differential Geometry. His academic advisor is the Nobel laureate Roger Penrose. So no question on his credentials. This book is wonderful because, as you can see, this already gives you a lot of understanding about general relativity, the Riemann curvature, and here you can see the happiest thought of my life, that is the equivalence principle, space-time metric, Schwarzschild solution, Einstein's field equation, and the greatest blunder of his life. All these things are covered, including gravitational collapse and black hole. All these are explained taking into account the concept of referential geometry. As I told you, this is again a collection of a very detailed book, which is this one. Again, I am putting the link. So the link of this video is given in the description box. That is number 4, where actually I have spoken much more in details about the concept, mathematics, relation to differential geometry, and given a review much more in details about each and every part of this book. So this actually clears up the concepts of understanding differential geometry, and the last portion is that a little bit about what is non-Euclidean geometry, and also a little bit on the history part. So what is non-Euclidean geometry? As I told you earlier, that a geometry traditionally differs from the Euclidean ones, and we unlock a great new mysterious world of new geometry. So Euclidean geometry, where the geometry starts by tweaking these geometrical parts, and non-Euclidean geometry actually has two parts. One is the elliptic geometry, where there are no lines that do not intersect. It has got a positive curvature, and hyperbolic geometry, where the curvature is something which is negative. Now, elliptic and hyperbolic geometry comes much before differential geometry and tensor. Question comes is that why do you need elliptic, I would say non-Euclidean geometry? Now, as I told you that the light cone actually presents in a great fashion, because this actually includes what is called the hyperbolic geometry. So in order to understand this, you need to know. Also, you can see this is the original diagram of a Minkowski. So you can say that a Minkowski model is embedded isometrically in a Minkowski space. That is, the hyperbolic distance function is inherited from Minkowski space. Also, you can see that elliptic geometry and general relativity is also related, although not in terms of true mathematics, but as elliptic geometry defines a positive curvature. So any type of a universe which has got a positive curvature, or a typical, I would say, an idealized conditions of geometry, includes what is called an elliptic geometry. So this type of universe is modeled using the concepts from elliptic geometry, etc. And elliptic geometry is related to general relativity, although Riemannian geometry is taken much more into usage, not much in details, but yes, elliptic geometry, the understanding, if you're creating a typical I wouldn't say isometric, I would say a positive curvature universe through which the solutions and models are taken, you need to understand what is called elliptic geometry and hyperbolic geometry, obviously. So what are the books that you would suggest? First would be Euclidean and non-Euclidean geometry by this famous person, Marvin J. Greenberg, who actually was a student of the famous Serge Lang. This is a wonderful book about Euclidean, non-Euclidean geometries, covering the history, development, hyperbolic geometry. A very good book. I would recommend you to go for this book. There is another book which speaks on the foundation of Euclidean and non-Euclidean geometry, because a good foundation would lead you to a better understanding of mathematics. This is a lesser known book, but this is very good. This is by Ellery B. Golas, and this covers a lot into the foundations of first the Euclidean and then the non-Euclidean. So this is the way the book has been organized: part 1 into elementary geometry, part 2 the foundations, and part 3 into non-Euclidean geometry. It's a very good book and a good understanding. The next book that I would recommend is Geometry Illuminated. This is also a kind of a textbook which gives you a very good understanding from the Mathematical Association of America, written by Matthew Harvey. And this book also is organized as part 1 neutral geometry, part 2 Euclidean, part 3 Euclidean transformation, because that is when the transformation from the basic flat geometry to non-Euclidean geometry starts. And this book specializes a lot on hyperbolic geometry. To know more about non-Euclidean geometry, I'm putting up a link. This is a fairly detailed video on what is non-Euclidean geometry, how the concepts, and a much more detailed understanding and reviews of those books. So I think that covers in details, although I understand that I have not covered all the mathematics much in details, but as I have given you links for those 5 videos, and this is in my playlist which is called How to Learn General Relativity. It is very detailed. You can go through all those 5 videos. You will be able to get a better and much more understanding. However, this video gives you a complete clarity in terms of the mathematics and how to learn process. So as you can see, I have divided into 5 different parts. First, you need to learn partial differential equation, then differential geometry, then non-Euclidean geometry, linear algebra, and tensor calculus. These are the 5 pillars of understanding general theory of relativity. So thank you very much for watching this long video. If you have liked this video, please do not forget to subscribe to my channel Physics for Students and click on the bell icon to get all the notification from Physics for Students. You can write to me for any confusion at this email ID, and don't forget to like to my other channel where I exclusively put up videos on general relativity. If you want, you can follow me on my Facebook, LinkedIn, Instagram, and Twitter account. That's all for today's video. I will be back, and Physics for Students will be back with more and more surprising and good videos and interesting videos. I will see you soon in the next video, but till then, goodbye.